Hi, relation between rational numbers and their decimal expansion. Now here, we will explore exactly when the decimal expansion of a rational number, say p by q, is terminating and when it is non-terminating, repeating or recurring. Now for this, let's take few terminating decimals and convert them into rational numbers. Let me consider three values. 2.25, first one. Second one, let's say 0.144, and the third one, let us say 1.715. Let's try and convert each of them in the form of p by q. Let's start with 2.25. For this, what you need to do is, you will write 225 and divide it by 100, right? One followed by two zeros. Why two zeros? Because there are two digits after the decimal over here. We can further write it down as 225 divided by 10 squared, because 10 squared is 100, right? A very, very simple thing. Similarly, we'll follow the same stuff for the second number as well as the third number. For the second number, we'll get 144 divided by 1000, because there are three digits after the decimals. We'll have three zeros in the denominator following 1. We can further write it down as 144 divided by 10 cubed. 10 cubed is 1000. The last number can also be written as 1715 upon 1000 or 1715 divided by 10 cubed. Right, three digits after the decimal, so you have three zeros which are following 1, and this can be written as 10 cubed. Now over here, we have actually converted them into the form of p by q, but still there are few common factors in the numerator and the denominator, if you see, in each of them actually. So let's cancel out those common factors, for which let's try and prime factorize the numerator as well as the denominator. For the first one, 225, the prime factorization is 3 squared times 5 squared. Now you know prime factors of 10 are 2 and 5, so 10 squared will give me 2 squared times 5 squared. This 144 upon 1000 can also be written as, in prime factorization form, prime factorized form I must say, 2 to the power 4 times 3 squared divided by 10 cube will be 2 cube times 5 cubed. Similarly, the last number 1715, the prime factorization of that is 5 times 7 cubed. 10 cube can again be written as 2 cubed times 5 cubed. Now over here, you can cancel out the common factors. So 5 square is the common part between the numerator and the denominator, so it'll get cancelled out. You'll get 3 squared divided by 2 squared. For the next number, you can see this 3 cube will get cancelled out by the power 4, and eventually you will have the numerator as 2 times 3 squared and the denominator as 5 cube. That is it. For the last one, you can see 5 is a common prime factor between the numerator and the denominator. So 1 5 will get cancelled out by this 3 over here. You'll get a 2 and on the power of 5. So you'll have 7 cube in the numerator and 2 cube times 5 squared in the denominator. Now what you can say over here, before I am telling you what is happening over here, a better idea is I must ask you, can you see a pattern out here? In the denominators especially. Yes, that is absolutely correct. So you can say that whenever any real number, these are three real numbers, which have terminating decimals. So all the real numbers which have terminating decimal forms, when being converted to p by q forms, all these forms are p by q form, wherein p and q both are coprime, which means they do not have any common factor between them. All the common factors are already being cancelled. So p and q are coprime numbers. So whenever terminating decimals are converted to p by q form, then the prime factorization of q, which is the denominator over here, will have powers of 2 or powers of 5 or powers of 2 and 5 both. Or we can say, we can write the prime factorization of q as 2 to the power n times 5 to the power m, where m and n both are non-negative integers. And this is again a crucial and important point, that these numbers should be non-negative. They can never be negative, but they can be 0, right? Because over here, as you can see, if I see the denominator, 2 squared is the only denominator I have. I don't have any component of 5, but we can include it in this form. 5 to the power 0 is 1, you know that. So the value of m over here could be 0 also, but it can't be negative. Similarly, if you see the second example, you can multiply this by 2 to the power 0. 2 to the power 0 again is 1. So it hardly matters whether you multiply it by 2 to the power 0 or not. So eventually you can say this n could also be 0, but it can't be negative. It will either be positive or be 0. Okay, so this is one thing, that whenever the terminating decimals are converted in p by q form, the denominator will always be of this form, 2 to the power n times 5 to the power n. Now, the vice versa of this is also true. What do I mean by that? It means, it's a very, very simple thing. It means just the opposite of whatever I've written over here. It simply states that whenever a rational number, say p by q, is converted into a decimal, you will always have this decimal as a terminating decimal, if the denominator of the given rational number is of the form 2 to the power n times 5 to the power m. And remember, we have cancelled out all the common factors. So it is expressed in the simplest form. Let me write it down in bold letters over here. In simplest form. So when the rational number is expressed in the simplest form, all the common factors are being cancelled out. Then the denominator, if that reflects 2 to the power n times 5 to the power m pattern, then the decimal you're going to get will always be a terminating decimal. Now you might be wondering that what will happen if the denominator is not of this form. Let's take a few examples out here. Let's talk about, let's say 1 by 7. If you see this denominator is not of the form 2 to the power m, 2 to the power n times 5 to the power m. It does not have 2, it does not have 5 as well. Therefore, 1 upon 7, you know how to divide 1 by 7, and you already know the answer. We have done it in one of the previous sessions as well. So it is 0.142857 bar, isn't it? This bar represents that this block of digits keep on repeating, or you say such numbers as non-terminating repeating numbers. Let me take one more example. Let me write down first of all. These numbers are non-terminating repeating decimals. All right, you can take one more example. For instance, 1 upon 3. Now 1 upon 3 is what? You know it very well. It is 0.3 bar. So it is again 0.3333, endlessly repeating. So it is again a non-terminating repeating number. Therefore, you can conclude with these two examples and many more such examples that whenever a rational number of the form p by q does not have this q equal to 2 to the power, does not have this q equal to 2 to the power n times 5 to the power m, then the decimal you're going to get will always be non-terminating. Will always be non-terminating recurring number. So bottom line, just remember this. In order to identify whether a number is a terminating decimal or a non-terminating decimal, you just need to see the denominator of the given rational number every time. Just see the denominator of the rational number given when the rational number is expressed in the simplest form. If the denominator is of the form 2 to the power n times 5 to the power m, it will be terminating. If it is not of that form, it will be non-terminating recurring decimal. So this was all about relationship between rational numbers and their decimal.